Hello. Oh, there she is. That was fast. Hello, Katie. Hello. 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 Good to see you. Hello, Josephine. Hello, Paulina. Hello, Maria. Hello. Hello, Alan. All right. They are afternoon. Good afternoon. Yes. Okay, wait. That's Katie, Josephine, Paulina, Maria, Alan. Awesome. Thank you. And good afternoon, direct chat person. Good afternoon, Alexis. Good afternoon, Jenna. Good afternoon, Emily. Good afternoon, Alan. Good afternoon, Stephanie. Good afternoon, Brandon. Good afternoon, Maria. Hello, Christina. Good afternoon, Katie. Good afternoon, Claudia. Awesome. Okay. And Shai is joining. All right, we can get straight going. I want to see one thing. Yeah, all right, so let's just get going. Pardon me for a second. Yeah, I want my goal for today. My goal for today is to start getting to is to get to those problems in homework 8 that people were asking very good questions about yesterday. Especially say, for example, the duck, the other duck in our life. Let me quickly, I'm gonna get let me just quickly finish the thing I was saying 2 days ago, because I think we ended it somewhat abruptly. So I'm gonna finish, so I'm gonna finish one thing we were just saying, and then get to homework 8. And I'm completing lead example because we used, and I know someone's here right now. Okay. I know we used this sled example. I attempted to use this sled example to walk through all of the steps that need to happen when you're solving a Newton's law problem. And I gather some of this was like review or refresher from things you did in lab, and some of it was an expansion or a deepening. But just for the sake of, but it's all sort of pointless if we don't finish it. So this is where we left off, I believe. We left off at the pure free body diagram of the sled. And that looked like this. So this was the pure free. And again, the situation is the one that I've been talking about for the last 3 days. All right, I guess just to remind you, here's the situation was sled of mass M on a rough ground being pulled by a string at an angle of theta. The sled was thereby accelerating along the rough ground at an acceleration, horizontal acceleration. And there's one more fact I can add to this thing. Now that we've had a discussion, somewhat of a discussion about friction, that came up 2 days ago. I can now tell you one more fact about this scenario, which is that we can also, since we've been saying the whole time that the ground was rough, and that's why I'm drawing it in that silly way with the jagged lines, we could describe the roughness of the ground with that coefficient of friction called mu. Okay, so that's the situation. And the goal of the problem, given these knowns, was to compute the magnitude of the acceleration A, right? So this was the problem that we've been talking about for like 3 days now. What we're up to is the pure, what we just had was the pure free body diagram. The pure free body diagram looked like this. The tension in the string was pulling up and to the right at some angle. the weight of the sled was pulling down. The friction from the ground onto the sled was pulling back on the sled. And we have a normal force up from the ground pushing up on the sled. That's the pure free body diagram. And that's where I think we left off. Or that's the last conclusion that we came to. What's the next step in any Newton's law problem? I'm just going to switch the screen. The next step in any Newton's law problem is then we have to choose a like our whole goal, the whole final method is to use Newton's second law to compute the acceleration, right? But the thing is, Newton's second law is a vector equation. So, and I've said this before, but now this is where this comes into play. To say that the force vector, the sum of all the force vectors equals the mass times the acceleration vector, is really to say that simultaneously yet independently along two axes, we have two equations happening. It's really to say this and this simultaneously yet independently, right? It's to say that the sum of all the x-axis forces produces the acceleration along the x-axis, while simultaneously yet independently the sum of all the y forces produces the acceleration along the y-axis. So what that means, and this is where, again, where I think we left off, what that means is that as long as we know all the forces acting in each of those axes, we can add them up and proceed. But we've got a picture here, as we often will with the pure free body diagram, we've got a picture here with forces that are acting neither along the x nor the y. Like we've got at least one force here who's just acting off on in its own direction. So our job is to create one last diagram called a component diagram. Our job is to zoom in on any, well, so I'm gonna write this. Our job, we must zoom in on any force vector which does not lie along an axis. Resolve. Oh, no, someone's here. 1 second. That vector. And so we must resolve, break up any vector that's flying off axis into components which lie along the axes, right? Again, I think I'm saying the same thing I said at the end of yesterday, but and so what we have to do is exactly the same thing that we practiced in the first unit of the semester. Like what we have to break, just like we did with displacement vectors or velocity vectors, we have to break up the vectors into components. So that means we have to know where our axis, we have to choose what we mean by our x and y axis. I've always strategy, we always choose a positive x-axis to lie along the direction of positive A. Like this is a key thing, by the way. It's down at the bottom of the sheet, but I'm writing it in a different color for a reason. I may have said it once before, but I will say it a million times. I mean, it's the subtle, vital part of this whole thing is that no matter how complicated the problem is, you stand back and you're invariably we're solving for acceleration, for acceleration. So you stand back and you look at the problem and look at what direction is acceleration going to happen in, the acceleration that I'm solving for. Which way, is it going to be that way? Is it going to be that way? Is it going to be that way? Is acceleration going to be on some angle, as it might be if, for example, the whole problem were on an inclined plane or something like that? Whatever acceleration is going to do, whatever direction acceleration is going to point in, you, in your mind, you line the x-axis up with that. And then you make the y-axis 90 degrees perpendicular to the x-axis. And that's your coordinate system. That's your graph paper in your mind through which you analyze all the vectors. So once you line up an x-axis with the acceleration, then you look in any vectors that don't fall on an axis, you got to break them up into axial components. So I'm saying in this case, we'll choose to make the x-axis, I mean, we're going to choose to make the x-axis the conventional direction in this case. What you might have done if I hadn't even said that, you're just going to make the x-axis horizontal. What I'm trying to say, though, is the x-axis is not always horizontal by any means. And that's sort of the key to all these problems. But in this case, the x-axis is horizontal. The y-axis is therefore vertical. That's my coordinate grid. So now, if we look at the pure free-body diagram, we see that the tension is the one and only force that is not lying along an x or y axis. So it's the one that has to be broken up it must be resolved into components. So that's what we're going to do. Oh, I'm just looking at the chat 1 second. Okay. Okay. So I'm going to zoom and stop me if you want me to go back. I'm going to, sorry. So I'm going to zoom in on that tension. The tension is going like that, according to my picture. There's theta, according to my picture. Theta is, well, there's theta. There's a tension. So I say, okay, if tension is pulling up and to the right, it's really pulling somewhat to the right and somewhat up. So this component, the rightward component is T cosine theta because it's adjacent. The adjacent component is T cosine theta. The opposite component is T sine theta, right? And now, so I've zoomed in on that. So we've resolved tension is the sum of T cosine theta and T sine theta. Like they're equal. This is important. Like what we just learned by breaking it up like that is that the job of tension, when the string pulls up on the sled up and to the right, that's literally equivalent in every physical way to someone pulling a string over to the right with some fraction of t. What fraction of t? Cosine theta times times t, while at the same time pulling up with some fraction of t. What fraction of t? Sine theta times fraction of t. Like I'm like literally what that triangle means is that that one big hypotenuse force is equivalent in every way to the sum of the two leg forces. Therefore, and this is the part that people often do wrong. Therefore, the reason I did that is I can now substitute those dotted leg arrows back into my original diagram. I can substitute them instead of the T. They do the job of the T. So I don't add, it's not in addition to the T, it's a substitute. So our component, therefore, our component diagram our component FBD, and this is the last diagram that we make, right? Like the process is you start with system schema, you get from that pure free body diagram. From pure free body diagram, you choose axes and get a component free body diagram. And finally, from the component free body diagram, you apply F net equals MA to each axis and solve for A. That's what we're doing here. And again, we're going to finish this finally soon and then do this procedure all over the homework. I mean, sometimes there's angles, sometimes there's not, sometimes there's friction, sometimes there's not, but it doesn't matter what elements you have. This procedure covers all the elements. Therefore, our component free body diagram is, oh, and sorry, something is in the chat, I think. Hold on. Oh, no, it's not. Okay. So the component free body diagram looks like this then. We still have weight coming down. We still have the normal force pushing up. We still have the friction force pulling to the left. But now we're saying that instead of that diagonal line, we have T cosine pulling to the right. And someone asked this yesterday. I mean, there's different sort of ways that you can draw two forces pointing along the same axis, but they certainly can exist. I do it like this. There's other ways you could do it. But this is now my diagram. This is my component FBD. This is everything else was done in order to get us to this point, because this is the only diagram that I can apply F net equals MA to. And again, I'm intentionally doing this big sort of complicated problem first, because I really want you to see F net equals MA looks like a really simple equation, but the complexity of F net equals MA is what do you put into the left side. Now we finally know, oh, and the other complexity of F net equals MA is recognizing that it's really more than one equation embedded in one. So now finally we have the information we need to fill out F net equals MA. So, sorry, I'm looking at the chat. 1 sec. Yeah. Okay, now that's a really good question in the chat. So my answer is yes. Okay, let me bet. In fact, let me make this a little bit more. Okay. What person in the chat is asking for or asking about? And in fact, I'm going to be more careful. Hold on. I'm going to answer the question in the chat. Let me just be. Okay. Well, the exact wording of the you can see it's not a direct chat. I'm sorry. Yeah. So, well, right. Okay. So good conversation. Like here, yes, these vectors are, first of all, definitively meant to show direction. Like that's their first job, is that they show direction, which the lines in the system schema do not. Like, I know this seems like a whole lot of pictures, but the system schema gets you one kind of information, and from that you build these free body diagrams, which finally are telling you direction. But yes, they're also telling you magnitude. Now with magnitude, it's like an estimate, it's a prediction, because our real goal in doing all this is we're doing a computation. We're ultimately going to get an answer for magnitude. At the end of the day, like, we don't know the exact answers for magnitude until we do the computation, but we have intuitions or predictions about the qualitative or the comparative magnitude, which I am trying to express in this diagram. Like, what I'm really trying to do, yes, so I'm trying to make some arrows bigger than others. I may be slightly off in how big they are, and I might even make a mistake. But what I'm really trying to do is anywhere that I think two arrows definitely are the same if I really think that I have active, explicit reason to believe that two arrows are the same magnitude, I'll deliberately try to draw them that way. And even there's a tradition, I'll even write this. A lot of people do this. If arrows are meant to be the same in length, a lot of people put a hatch mark on them. I think that's what it's called. Like, I'm not doing it here. I mean, they would go like that or something on both arrows if they thought they're supposed to be equal. But I do, but I don't think any of these are meant to be equal. And that's actually the thing that I am trying to explicate here. Like, I'm glad someone's asking. Like, we'll see in a minute when I do the analysis. But I deliberately don't want you to think that, for example, I am very confident that that MG arrow should be longer than the N, the normal arrow. They definitely should not be the same length. Now, I don't know if it's as dramatic as I just drew it here, but the N arrow and the MG arrow in this diagram should not be the same length. And I'm sort of exaggerating that fact because it's a common misconception. It's easy to sort of fall into a habit of thinking that they are. What you'll see in a minute when I do these calculations, hopefully, is actually what I'm trying to express there. What I really think is that the sum of the lengths of the N arrow and the T sine theta arrow, I think those arrows added together in length should be equal to the MG arrow. Now, I'm going to say that again a different way in like 2 minutes, but hopefully that makes sense to some of you. That's what okay, cool. Okay, so I'll leave it at that for the moment. But yeah, I mean, this is definitely a good question. And again, I'm intentionally starting with this one big mama problem that sort of involves everything at once, so you can see everything at once. But yeah, all right. So I'm going to go on now. At least I think so. Thank you, Maria. I keep thinking everything is private. Not everything is, and it's good. It's helpful that it's not. So thank you for asking that and closing the loop. So okay. So what do we do now? Okay. So now, yeah. Hello. Okay. Now we are ready. Finally. To use F net equals MA in order to compute A. Now, the key is that F net equals MA really is two separate simultaneous equations. Okay, note this now. This is a subtlety. If we set things up correctly, if we chose our coordinate system strategically, I should say, then A will always point along the x-axis. Like we chose the x-axis for that to be the case. Therefore, and now I'm talking strategy now. There's other ways you could do this now, but I highly recommend, since we're going to do equations along two axes, what I strategically recommend is that we always start with the y-axis. Always start with the axis that you don't care about, so to speak. Like the axis that you're really solving for in the end of the day, leave for the end of the day, because you're going to get information from the other axis that you're going to need most likely for the final axis. So here's what I do. So therefore start with y-axis. Now that's a strategy. That's not a law, but it's a pro tip. So what do I mean by start with the y-axis? I mean, I'm going to say the sum of all the y forces equals the mass times the acceleration along the y-axis. So I'm finally plugging in. I'm finally ready to plug in for that left side. All of this work was to know what to plug in for the left side. And what do I plug in for the left side? I look at my diagram. Well, here, I look at my diagram and I look at the y-axis and I see that there are 3 forces pointing along the y-axis. We'll call, I should have done this from the start. Call up positive and down negative, and for the right, for the x-axis, call right positive and left negative, or make whatever decision you want, but make it and stay consistent with it. So I look at that y-axis. I've got 2 forces pointing up, and I've got 1 force pointing down. The whole idea is F net means add up all the forces. So I'm going to add up all the forces, but I'm going to account for direction. So in the y-axis, I literally say n plus T sine theta minus mg, all that equals ma on the y-axis. That is my statement for the y-axis, right? Honestly, I don't know if that looks simple or complicated to you, but I can tell you this, there's no way I ever would have come up with that unless I had this diagram sitting here. But once I have the diagram, I'm just reading it off, right? I'm literally saying, oh, there's 2 up arrows and a down arrow, so there's 2 positive signs and a negative sign, and they're being added up, and that's it. Right? That is the y-axis. Now, I'm going to analyze that a little bit before I go. I'm going to play with it a little bit before I go over to the x-axis. I look at that. Now, my ultimate goal with all of this is to use forces in order to get acceleration. But we're using forces in order to get horizontal acceleration, ultimately. If I look at this axis, I believe here, it's the reverse. I believe here on this axis, I know something about the acceleration, and from that, I can infer something about the forces. That is to say, in this axis, we know from the start that the acceleration is 0. Right. And think about, this is why we set things up the way we did. The sled, I'm not saying the sled's not accelerating. I'm saying the sled is accelerating along the ground. That's the premise of the whole problem. The sled is not flying up into the air or breaking through the ground. So on the y-axis, there's no acceleration. That's a fact that we know for the problem. Honestly, if you're following this will always, if you do things the way I'm suggesting, if you set up an x-axis that lines up with your acceleration, then there will always be 0 acceleration along the y-axis. Like you can sort of rely on this if you do it with this strategy. So I'm on this axis, I'm using acceleration to learn something about the forces. What am I learning about the forces? Well, I mean, if A is 0, then n plus T sine theta equals mg. And this goes back to right there is Maria's question, or I mean, is my response to Maria's question. That shows me that what is balancing the weight of this sled? If the sled is balanced, if it's not flying up or crashing to the floor, the ground is to some extent supporting the sled, but the ground is not the only force supporting the weight of the sled. The rope is also pulling up on the sled. Together, between the ground and the rope, together, they are supporting the weight of the sled. Now, that's really important. It's really important. It suggests many things. I mean, it suggests that if the rope weren't there, the sled would still be supported on the ground. It would still be sitting on the ground. So if the rope weren't there, then the ground would be doing all of the support. In other words, apparently the ground adjusts how much it pushes up on the sled depending on what is needed. This is what I was saying 2 days ago. This is a tricky subtlety. The ground doesn't just do an automatic, there's no formula for what the ground does. The ground pushes just enough to keep the sled there. And if someone starts pulling up on the rope more and more, then they're picking up the slack, and I think you get what I'm saying. So So you don't want to memorize that the normal force equals anything. When you find that the normal force just it equals what it equals in order to keep things balanced. In other words, the normal force will support the weight, but minus whatever help it's getting from the vertical tension of the string. That's what that statement means, right? Now, why did I... Now, you'll notice that I'm not done with the problem, and I don't know if you can read my handwriting. I might have to write this again, but I'm about to move to the x-axis now. You will notice, and this is not always true, this is a common procedure, that the way I've set things up, I first looked at the y-axis, I used the acceleration on the y-axis in order to get some knowledge about the forces on the y-axis. What specific knowledge I just got from the y-axis was I just got the magnitude of the normal force, or at least how it's related to other things. That's generally, or if there's a normal force involved in the problem at all, that's generally what you're trying to find out from looking at the y-axis, is what is the magnitude of the normal force expressed in terms of knowns. The reason that we do that is because now I'm going to turn to the x-axis. Now we're going to turn to the x-axis, which is what I really ultimately care about. And just to cut to the chase, the x-axis is going to involve friction. And remember, we said 2 days ago, and I think also last week, friction only ever arises due to a normal force, right? The whole idea is friction and normal are intimately related. The harder you press down on something, the harder it is to rub two things together. In fact, specifically, what friction is the product, the multiplicative combination of roughness with pressure, right? So the more there is this, the more there is this. So we needed to know that normal force so we could, in other words, the equation that we learned 2 days ago is that friction equals mu times the normal. So if we want to know the friction, we need to know the normal, and we don't automatically know the normal without analyzing the diagram. So we've done that. Now we can go to the x-axis. If we look at the diagram again, so in the component diagram, we have, here it is, we have t cosine theta pulling to the right, and we have friction pushing to the left. And they're not equal. Those, I mean, I just flipped it, sorry, fast. But back to Maria's question again, and Katie's response, those two arrows, I don't have any reason to assume they're equal. If they were equal, I mean, that could be equal in life, but then the sled wouldn't accelerate at all. And the whole premise of this problem is that the sled is accelerating to the right. So what I think we have is t cosine theta to the right minus friction equals ma to the right, right? Let me just get rid of this. Okay. Okay. Right. So now what do I do? Well, friction okay, so now we have to compute the friction, or at least we have to express friction in terms of things we know. I want to just remind you, I'm just looking at the time. Okay. Just to remind you of what we said yesterday, 2 days ago. The force of friction equals mu times the normal, right? I just want to, let me think for a second. Yeah, okay. Okay, quick sidebar here, something that I I just want to mention now, so you know it. I'm going to use this equation, F equals mu times the normal. We need it for the rest of our lives. Truthfully speaking, there's fiction can fall into one of two different cases or two different categories. Friction can be acting because things are already sliding, already experiencing motion relative to each other that's being resisted by friction, or friction can act so as to prevent the sliding in the first place. In other words, there's two cases of friction. And what we're dealing with here is one of them. We're dealing with friction when things are already in motion. And this is called kinetic friction. Sliding friction. When this is occurring, and that's what we're talking about here, when something's already sliding relative to something else, then specifically we put a K next to the F to mean it's kinetic friction. And the roughness that it's based on is called mu sub K. The roughness of the coefficient of kinetic friction. I'm just being technical here for a second because you need to know. But this is this is all as opposed to sorry. Case number 2 is called static friction. When one surface is holding another in place. And then in that case, what's operating is something called Fs. And the maximum that static friction can ever be is the coefficient of static friction times the normal. So this is a slight sidebar technical point. I'm just saying it's always one or the other at any time. It's never both at the same time. Things are either experiencing static friction or kinetic friction. When they're experiencing static friction, you use the static coefficient, which you would be given if it's relevant. And when they're sliding, you use the kinetic coefficient, which would be given if it's relevant. And so we're in the case right here where it's kinetic. So technically we're using, when we say mu here, technically we mean mu sub K. I'm just saying, wait, hold on a sec. Wait. Oh. Oh, okay, great. I'm seeing something in the direction. Good. If this is help, and I know this is all, again, as always, if anybody is learning from this right now, if you thought about the homework and you're seeing that this is correct, that this is like making you realize that you didn't understand something on the homework and now you understand it. To everybody and anybody, I'm saying that's a good thing. Like, believe, if you're relating this in any way to anything you did on the homework, even if you did it wrong, then that's all the more reason that it's good. It means it's good that you tried that in advance, so now you have a reason to be paying attention now. It means that this is landing somewhere, honestly. And if you, and all of you, remember, if you find out that you did things in the homework that are wrong, but before or after I look at it, you can re-upload, all of you, always. Like, I'm very glad that people are being so attentive to the homework, but don't be upset if this means you did something wrong. If that means you now understand it, first of all, that's just good. But second of all, you can re-upload corrections to homework and get more points. As long as the portal is open, all of you can do that. And please do. If you, it just makes me, and again, if you're thinking, well, if I had done the homework now, I would do better now, but you wouldn't be paying attention as well now if you hadn't tried to do the homework before. So something is working if at least one person in the room seems to be saying, oh, now I get it. I didn't get this before. Good. I mean, not good. Okay, but I'm going to go on. And I will get to the, all right. So this is a sidebar that's also in the notes from it. So I just had to be clear because yes, and in the lab too, there's like different cases of friction. So I'm just trying to lay them out right here so you have it, but it's always one or the other. I'm not saying, by the way, I'm not saying to anybody that they can't both come up in a problem. Like, the common situation is that something tries to hold something in place for a while, and then so it fights against the maximum force of static friction, but then it eventually fails and the things start moving. So in life and in a physics problem or in a physics experiment, the friction can change from static friction eventually to kinetic friction. And in fact, that's generally what happens. I'm just saying they're never both literally at the same time. Like, you're analyzing one case and then you analyze the other case. Okay, now in this problem that we're doing right here, it was already assumed the thing had already gotten in motion by the time we started the problem. Like, we're not having a fight with friction here. It's just already sliding and the friction's there. So back to this problem. So here, assuming we are all believing that here it's kinetic, here it's sliding friction. So that's the kind of friction it is. And so technically speaking, the mu that was given would be the mu sub k. Like, often in these problems, you're given both mu's and you choose which one to use when. Okay, so now I can finally go back and say, therefore, T cosine theta minus mu k times the normal equals ma in the x direction, right? Which is all of the a that we're looking for, right? That's what we have so far now from the x-axis, right? Now, what's the normal? Well, that's why we went to the y-axis, because both axes are happening independently but simultaneously. Like, whatever we learned about the normal force from one axis applies to the other axis, right? So from y-axis, we said that the normal force equals mg minus t sine theta, right? So we substitute in. That's why we did all this. I mean, it is what it is. And again, at any moment you want me to go back, please let me know. I'm just trying to. So we go t cosine theta minus mu times mg minus t sine theta, all that equals ma, right? So now we're finally almost there. In other words, okay, and what are we solving for? We're solving for a. So divide both sides by m. A equals t cosine theta minus mu mg plus mu t sine theta all over m. And that's as good as that's it. That's our answer, because I never gave you any numbers for this problem. I just gave you letters. That would be our answer. It may look fairly complicated, but say these were the givens, right? I'm just looking at the time. Yeah, okay. Oh, wait, something in the chat. Wait, sorry. Oh, no problem. No problem. Okay. Okay. That would be the answer. Okay, there's more that we could say about that problem, but there's more that we could say about that problem. But I think I've said enough for the moment. Obviously, I want to turn to the homework, which I know is what most of you want me to do. What I want to just stand back and look at this problem for a second, though. Like, that's a big problem, right? I mean, we spent a long time, we did a lot, because there's a lot of forces involved. Because I intentionally made a problem where kind of like every possible force you generally comes up is involved, and that there was at least one angle involved. So sort of all of the elements of a Newton's law problems are all in there. So it got complicated. Now, hopefully, when we turn to the homework, like some problems will have some of these elements, some other problems will have other elements. We have to make decisions, but that's the procedure. Okay, to summarize one last time, you do a system schema to figure out what the forces are. From that, you do a pure free body diagram to see what direction the forces are acting in. Then from that, you do a component free body diagram to get exact components along X and Y axes. And then from each axis, you do F net equals MA to solve for A. Like, that's the procedure. So please do ask questions if there are any, I mean, or as we go, but that, again, that was end of example problem. That was all a end of large example problem. So now let's turn to the homework.
I have a question.
Yes.
So on the homework, there's on the last part, there's the two boxes that are moving horizontally on the table and there's friction. Would the vertical normal force just be the combined mass of those two? Well, like, would the normal force vertically be unaffected by the horizontal force? Because I know there's friction, but I'm not entirely sure if that somehow indirectly or directly affects the vertical normal force of the
Wait, that's a perfect question. I believe that I totally understand what you're asking. And in fact, it might be slightly two questions, but that's a great question, Claudia, and everybody. And yes, I'm not going to do that problem first, but the summary answer is yes. When you've got those two blocks at the end of homework 8, and they're sliding along and one's pushing against each other, the normal force up from the table is unaffected, like you're saying, unaffected by anything horizontal. You are correct. Okay, so first of all, yes, you're correct. The upward normal force in that situation on the homework is supporting the entire weight of both of the both of the blocks. And since nothing else vertical is happening that I remember, there's nothing else involved in that opposition. So yes, you are right. The upward normal force from the table would support the combined weight of both of those blocks. You are right. What was the other thing I was going to say? And that's very good that you realize that. And yes, like in general, to expand on that, the reason we're doing all of this and getting the components and all of that is that, right, we believe that whatever's going on like this is not affected by whatever is going on like this, and vice versa. The link between the two, ultimately, the link between the two axes is friction. Like friction is the one thing that sort of says whatever's going on from the normal affect I'm saying too much. Friction is the one phenomenon where we say, however hard two things press against each other does affect how they rub a slide against each other. So normal affects friction, but you are correct to say nothing affects normal besides whatever's on its axis. I definitely said too much, but my answer is I agree with what you said, and it's a good point. Okay, wait. So I'm gonna go to homework 8 now. I'm just looking to chat with. Oh, did I flip? Oh, okay. So okay. So now homework 8. Now, even in homework 8, of course, I'm going to skip around. I'm not going to do every problem. I'm going to do like the big ones or the hard ones or the ones that people are asking questions about. And I know we only have 20 minutes. So hang on, bear with me for a second and let me choose. Whoa, hello. Okay, here we go. Okay. You know what? Actually, there's maybe many. Okay, there may be many things we have to do on homework 8, but I actually think, given the good questions that you guys are asking, and given where we are in the course, I'm going to skip right now. Well, am I? Hold on 1 second. Right now, just because people are asking about it, yeah, I'm going to start with the duck in the elevator. I can go back to other problems if people ask, like next week or whatever, but let me go. I'm going to start with the duck in the elevator because people asked about it, and I think we're at that level at this point. And again, this also means all the other problems you could turn in for credit, and you still can, even if you haven't yet, or you can correct them if you now realize that you've done things wrong on them, et cetera, et cetera. Okay, so this is a duck in the elevator. Apparently, I really do like ducks. Okay. Okay. Okay, the duck has a mass of 18. The whole elevator cage has a much larger mass of 200. You're given an acceleration. Okay, let's call up positive. Let's call down negative. The acceleration is going up at 15. The velocity is positive 50. Okay. All right. So first of all,
Isn't the arrow for the velocity pointing down?
oh, sorry. How you? Oh, sorry. That's my bad. Thank you. Thank you. Yeah, that's weird that I did that. Sorry. Thank you. You're absolutely right. And put in a portal for that. I mean, put in for points for that. Yes. Thank you. Okay. All right. So first of all, we want a system schema, and we want a system schema for the situation, but the duck is the mass of like is our object of focus. The right. The duck is the thing whose acceleration we're ultimately trying to compute. So I draw a dotted circle representing the duck. And the first thing I do is I say, no matter what, the center of planet Earth is definitely an object that's pulling on the duck, because the center of planet Earth always is. And I don't care where in fact, just even to make this really, sorry, I could draw the center of Earth anywhere, and just to really emphasize that I'm going to draw it up there. I don't care where I draw it, but it's definitely pulling on the duck. Now I draw an object for every, I draw a solid circle for every single object that is touching the duck. It's, oh, sorry. Oh, sorry, I see something in the chat. If you already know that you've done things wrong in the homework, or if you don't even wait for feedback. You can leave the old draft if you want me to see like how hard you're working and all that. Just make it clear which draft you want me to like actually read first or whatever. If there's just like a minor correction, then you might as well wait. But if you think, oh my God, I did like 3 problems wrong and don't even wait for me. Sure, right. Okay. So the center of Earth is definitely pulling on the duck. What else? Anything else that's touching the duck? Well, the floor of the elevator cage is touching the duck. So that's an object. So we've got like the elevator cage, or the floor, so to speak. The elevator floor is touching the duck. So that's an object. And the problem specifically says that the cable that's making the elevator do its thing is not touching the duck. So it's not touching the duck. So that's not a force on the duck. So those are the only objects touching the duck. So now I just connect these things with lines. Well, I do the one touch, one line rule with the 2 exceptions. That is, the exception 1 is the Earth always gets a line even though it's not touching. And then the elevator floor, now this is a little bit subtle, and I think Maria asked about this 2 days ago. The elevator floor is a surface pushing against the surface of the duck's feet. When surfaces are pushing against surfaces, in principle, you want to always consider the possibility of 2 lines, right? One that represents the normal force, the pushing of the 2 forces against each other. But then if the surfaces are at all rough, if friction is going to play any role in the problem at all, you're going to draw a second line to indicate friction. Like that would be the tradition. And if this were an exam and you drew a second line right now to indicate friction, I would not take off points. Like that would be my recommendation, in fact. However, this problem does not say anything about roughness at all, and there's never are we acknowledging any roughness, nor never does it mention any kind of like lateral movement of the duck. It's not going anywhere in the x-axis. So it seems like in this problem, the surfaces are smooth and friction's not relevant. So I don't even have to put that line in. Okay, but that's a judgment call. Like, I don't think I'm going to end up using friction at all. So I'm not putting that line in. But it's a good habit to be in. So I'll even go like this. Like if you put a second line in for friction and or an exam, it'd be fine. It's like the right tradition to do. But anyway, that's my system schema, I think. So then the second thing is now using, so now in that system schema, there's definitely 2 lines. So there's going to be 2 forces on this duck in the pure free body diagram. So sorry, this was system schema. This is now pure FBD. So I draw a dot. There's definitely mg down on the duck. That's the line from the center of Earth. And now that line from the elevator floor is the normal force up from the floor. Now, I'm predicting, this is again back to Katie's thing from before, and Maria, I'm predicting that normal force is going to be bigger than the weight. I don't think they're going to be equal. And the reason I don't think they're going to be equal is because this duck is accelerating up. I mean, we're told, well, how could the duck accelerate up unless there was a net force pushing the duck up? Where would the net force come from? Well, the floor must be pushing harder on the duck than it must be pushing more than just supporting the weight to support the weight anyway. So I think the normal force is going to be bigger, but we'll see in a second. All right, now line 3. I mean, part 3 of the problem, it asks for the action-reaction pair, the Newton's third law pair implied by each arrow in the duck. I mean, by each arrow in the free body diagram. What do we, okay, Newton's third law says, if I push you, you push me back. Newton's third law tells us that every single force is a symmetric interaction between two objects. That's the point of that. It's an interaction between two objects, and it goes in both directions, just like velocities do. So what they mean, so I look at each force. So if there's two forces in a diagram, there's got to be two action-reaction pairs. Every arrow in the diagram is an action that implies some reaction in some other diagram somewhere in the world. Hold on, someone's here. Okay. In other words here, okay, pair 1. Pair 1. The Earth pulls down on the duck, right? That's what that mg gravity arrow means, that the Earth is pulling down on the duck. So that's an action. That's the action. Therefore, the duck pulls up on the Earth. That's the reaction. Let's pause on that for a second. I'm saying now that's one arrow. I'm saying one arrow in our diagram is an action that implies or means that there's that reaction necessarily happening. Let me put this another way. That is not both the arrows in the diagram. That is a full description of one of the arrows in the diagram. Let me say this even more clearly, or try. Even if an object were just in free fall, even if the duck were just falling and there was only one arrow in its diagram, even if something's just free falling, I would say the Earth is pulling down on the thing, and therefore the thing is pulling up on the Earth. Every force goes in both directions. Every force is a symmetric interaction between two objects. So, oh, cool. Okay, cool. So, that's really awesome that you see. Okay, so that's pair 1 from arrow 1. That's the pair implied by the word gravity. And notice, by the way, I didn't use the word gravity in either of these descriptions of action reaction. I say the Earth pulls, and this goes back to the system schema, in other words. Look in the system schema. This is saying one of those lines means it's a tug of war. Earth is pulling on duck, duck is pulling on Earth, or whatever. Earth is pulling on duck, duck is pulling on Earth. And it's a tug of war between two actual objects. Like what we don't say here is like, we don't say duck pulls up on gravity. You don't say gravity pulls down on the duck. and therefore the duck pulls up on gravity. You can't pull up on gravity. That doesn't mean anything. How do you pull up on a pull, right? It's the earth. So every action reaction pair has to have the word pull or push in it, has to have a direction in it, and has to have two actual concrete objects in it that are interacting with each other. So that's pair number one. Pair number two, from the other arrow, from the normal force, pair number two is the floor pushes up on the duck, and therefore by law necessarily the duck pushes down on the floor. This is what we're trying to say. And I'll move on, but this is one of those subtle things. This is not numbers. This is a concept, but it's a very important concept, and it is a subtle concept. Notice we are not, those arrows in the diagram. This is a long way of saying don't assume that those arrows in the diagram are equal and opposite. Just because they're opposite doesn't mean they're equal. And just because they're opposite, or even if they were equal, doesn't mean that they are Newton's third law. In fact, two arrows in the same diagram are never Newton's third law. Newton's third law means that for every one arrow in one diagram, it has a mirror image that exists in some other diagram somewhere else. Think about that, like really. But okay, so that's the action reaction pairs for that. Okay, then it says, okay, and so this goes back, this is the important thing, this is sort of like just for the record, notice that in the last 2 days that anybody's asked any questions, I mean, like about these homework things, when people were asking questions 2 days ago about this duck thing, and I think Claudia was one of those people, then people were asking questions today, and not to, but then Claudia had a question today that was on a totally different problem, right? She was asking a question on a problem that we'll get to, but notice the theme in a lot of these questions, the theme is like, how do you handle the normal force? The normal force is one of the challenging issues of all of this. You can all do it. It's not meant to be a mystery. But the first thing I'm sort of proud of is that people in the room are noticing that the normal force has to be thought about. You are correct if you think you've got to give a little extra care to the normal force. And what you never wanted, and so again, this is a compliment, like I think you guys are right in the questions you're asking. Like what you don't ever want to do is just assume that the normal force, you don't want to assume that the normal force equals the weight because of Newton's third law or something like that. Like that's what we're sort of trying to emphasize here. So now it says in part 4, compute the magnitude of the normal force. How can we do that? We're going to do it the exact same way we did it in the sample problem. Like, we now have a pure free body diagram. We have a pure free body diagram. What we would want to do is turn it into a component diagram in order to do F net equals MA on each axis. But luckily, we don't even have to, luckily, everything already is on one axis here. Like everything is already lying along coordinate axes, like in this case, one axis, the y-axis. So we don't have to. We have components already. So that's good. So we don't have to make a new component diagram. So we can say F net equals MA, specifically F along the y-axis, F net along the y-axis equals MA along the y-axis. That's the only axis that anything's happening. So we can say, we look at our diagram. Here's our diagram. It's very simple, right? N up minus mg down. I mean, we'll call this up. And we'll call this down. I mean, we'll call up positive, we'll call down negative, right? So it's seemingly simple diagram. That's nice. So we literally say N up plus mg down. So mg gets a minus sign equals MAY, right? And here we were told, just like before in the other problem, we knew the acceleration we plugged it in to get the normal force. Same thing here, only here it happens that the A is not 0. So we literally say N equals mg plus MAY. Note, we're going to end here at this point. Note, again, the normal does more than support the duck's weight, right? Like in the sled problem, the normal force did less. It had help from the string. It did less than support the weight. Here, the normal is doing more than supporting the weight. It's supporting the weight and accelerating it up. Like the normal does what the normal does. Normal does more than support the duck's weight. It accelerates it up. Well, so we say, I know we're just about done. So N equals mg plus MAY. Well, M equals 18. G is approximately 10, like 9.8, but I call it 10 a lot. You can do the mass is 18. The acceleration is 15. Notice the big 200 is not relevant here, and neither is the velocity. Those, if they are relevant at all, they come in later, but they do not affect this calculation. So 180 plus 220, I think 18 times, but you might want to check that. I think yeah. And we have 3 minutes left, so it's okay. Oh, 27. Where did I get that? Okay, sorry. And that's the answer, right? The normal force has to be a lot bigger than the weight of the duck. The weight of the duck is 180 newtons. From the perspective of the ground, just to finish the problem, I guess, from the perspective of the ground, how far will the duck have traveled after 7 seconds? Well, that's where the velocity comes in. Like x equals 1/2 at squared plus v. So this goes back to regular physics, and that's the whole point. 1/2 15, 7 seconds? So, and v naught, they said, was 50 times 7. So 49 times 15. This is the last thing we're doing today. I do see the time, 49. Okay. So for what it's worth, that's what we've done today. I mean, we'll do more, obviously. I'm not assigning any new homework right now. Let's just stay on this for now and catch up. I'll catch up with your exams. You catch up with this, and let's just keep on rocking in the free world. Wait, I can't. So, and we're not. What would MG? Oh, sorry. What would MG? Well, MG means literally M times. Well, M is the mass, 18 kilograms, and G is the downward free fall acceleration due to gravity, which we often call 9.8, but we're free to round to 10 meters per second squared. Mg is mg is the weight. Well, the G doesn't stand for grams, but the G stands for the acceleration due to gravity. So mg is the force of gravity on an object, the weight of an object, and it's always there in every single one of these problems. It's the downward pull of the center of the earth on any mass. I could say, but I don't know if that answers you. But mg is weight, mass in measured in kilograms times free fall acceleration measured in meters per second squared. But you're all free to go. I mean, I'm going to hang out if there's any more questions. Oh, okay. Bye. Yes. Have a great weekend, everybody. Have a great weekend. Okay. I will. Thank you.